Okay, folks, last time. So Olivia is studying the heights of a rare species of tree in the Amazon, which are normally distributed with a mean of 100 feet and a standard deviation of 15 feet. She wants to find a tree in the top 1% of height. How high does the tree need to be to qualify? Aha! So all of a sudden, this is the only problem that we've got in this whole set, which works the other direction. We have a probability, and we need to work back to an actual value. So we have to find x. And we want top 1%, so it looks like we're going to find x given the probability above. We could have, because if it had been phrased top 99%, it would have been the other way. But anyway, they're equivalent, so we'll work with that. So now we're going to use this, the norm.s.inverse. So we're going to start with a probability, use norm.s.inverse to get a z-score. And once we have a z-score, then we can calculate x. So investigator is Olivia, the subject is tree height. And so what's the case? We said it was one-tailed right, and the mean is 100, and the standard deviation is 15, and the probability of x was 1%. All right, and so now we're going to get a z-score using norm.s.inv. So now we're doing the inverse function to work from a probability back to a z-score. And this is going to be wrong. And the reason that it's wrong is because all these functions look left, but our 1% was looking right. So we got to toss in the 1 minus. This time it's inside the parentheses. If you're wondering why are you sometimes out here, why you're sometimes inside, it's because the 1 needs to subtract the probability. Since the probability is in here, you got to do it. Whereas when we had it outside, it's because the whole outside part was calculating a probability, which we then subtracted from 1. Okay, so the z-score is 2.33. So now what value corresponds to 2.33, and that's where we use this. It's going to be mu, so it's equal to mu. And this kind of makes sense, so I want to stop for a second and explain why this makes sense. So it's mu plus the z-score times the standard deviation. Why? Because the standard deviation, which is 15, right, is the average distance from the mean. The z-score tells you how many standard deviations you are from the mean. So if you multiply your z-score times that 15, you're going to start out at the mean, and now you're going to add to it a certain number of standard deviations, 2.33 of them in particular. You're adding, and that will get you the tree height that you want. So it's going to be the z-score times that 15. So there's the tree height that we're after. All right. And you can see right here, that's really pretty high, right? I mean, you're at the high end of the distribution, you're at the high end here. Probability of a tree height that high is just 1%. At the 2.33. In other words, there's very few trees higher than us. You can see this tiny little bit of green peeking out here. There's just very few trees higher than us. So where does Olivia's tree height fall relative to the average? Well, it's in the top 1%, which is, after all, how the problem was phrased. And then you've got some questions to answer here, and then you'll be all set. And that is our lesson in probability. Just to review, though, remember, the little dots, when you see a column of little dots, all it means is lots of observations at that x value. And there will be always more in the middle of the bell curve, more dots, than there are in the tails. And we're going to use that difference to decide when we do hypothesis testing, whether something is likely to happen or not. Like, you're not likely to find a tree this high, right? But you are likely to find a tree right around here. And that likelihood is going to become the basis of hypothesis testing. So it all fits together, as you'll see in our next unit. Take care.